Okay, so this last thing that we're going to do is we're going to talk about atomic spectroscopy. And remember, an atomic spectrum is where you take the light when you're burning an atom, you run it through a spectrum, and you're going to get something that looks like mostly black, and it's going to have a few lines. So let's interpret what that means. What that means is each wavelength, so that would be each line, the wavelength associated with one line that you see in the spectrum, is the result of an electron that is transitioning, an electron transition between two of those quantum mechanical orbitals. So what ends up happening is an electron absorbs energy and it jumps up to some higher energy level. Higher energy levels are by definition more unstable. And atoms want to be, just like all particles, we want to have the lowest potential energy possible. So it goes up to a higher energy level. That's unstable, so it's not actually happy there. So then it's actually going to fall back to a more stable, lower energy orbital. And when it does that, it releases this energy as light or radiation. It depends on the wavelength where it falls. If the radiation falls within the visible light spectrum, we can see it and we perceive it as light and a color. If it happens and it's outside of visible light, we don't see it. All right, now let's look at it visually. Visually, these are energy levels. 2 is higher than 1, 3 is higher than 2. As you go up, these have higher energy, and so that means these are going to be more unstable. They're not totally unstable, but they're more unstable, and this is going to be more stable. So let's take this electron. Here it is, energy level 1. It absorbs some energy from somewhere, and it says, hey, I'm super excited. It jumps up to level 3. It says, oh, I can't stay here because I'm not as happy. It's unstable. So then it falls back, and if it falls back here to energy level 2, the difference between these two we see as light or radiation as it falls back. Because remember, electrons don't just whirl around arbitrarily. They occupy specific addresses, so which we determined by quantum numbers. So you have to understand quantum numbers to understand this equation now. So we can actually use an equation. The radiation that we see or don't see, the radiation that is released, is a result of the electron changing its principal quantum number. Now you should remember that the principal quantum number is n. So principal quantum number is n. Now we will only be doing this for hydrogen atoms. Here is the equation. Delta E equals RH times 1 over NF squared minus 1 over NI squared. Just write that down. So delta E is an energy change. RH is what we call the Rydberg constant for hydrogen, and that is equal to negative 2.18 times 10 to the negative 18th joules. NF is the final energy level, and N sub I is the initial energy level. So when you're working these problems, make sure you identify that, just like when we were doing heat calculations, we identified and labeled our initial and final temperatures. So let's talk about the signs here. Explanation of the signs, because notice this Rydberg constant is negative. In this concept, the atom is the system, everything else is surroundings. So a negative sign means energy is released from the atom. So here we're cooperating with thermodynamics. Energy is leaving the system. A positive sign means energy is absorbed by the atom. So you have to be careful with your signs here. You're going to be dealing with fractions. So let's say that we're going to a higher energy level. If we're going to a higher energy level, so like if we're going from 1 to 2. So 1/2 is less than 1. So you're going to get a negative number here. A negative times this negative is going to be positive. That makes sense because it has to absorb energy to go from 1 to 2. Consequently, if it's falling back, 2 squared over here, so 1/4 is less than 1, so you're going to have a positive number. So you'd have a negative delta E, which makes sense that energy is released. So be careful with the signs. The signs matter. They only tell you direction. It only tells you direction because we're going to end up having to drop the sign because you have to know whether it's absorbed or released. But either way it goes into or out of the atom, that occurs by light, which is delivered in photons. And so we're going to couple this with our energy of the photon equation, which is h over frequency, or hc over lambda, because most of the time we're going to be calculating the wavelength of the light that's going to be emitted or absorbed. So here, let's calculate the lambda that's emitted. We're only going to be doing this for hydrogen because this equation only works for hydrogen. Moves from n equals 3 to n equals 2. So this here would be n initial. This here is n final. It's going down. So energy should be released, so it should be negative. So delta E R sub H 1 over n final squared 1 over n initial squared. You don't have to try to memorize this. It will be given to you. All right, so let's plug this in. I don't have RH stored in my calculator because we just don't use it that often. It's also always going to be given. So negative 2.18 times 10 to the negative 18th joules, 1 over n final, so that's going to be 2 squared, minus 1 over n initial, so that's going to be 3 squared. You can do these in your head, the squares, or you can just do it in the calculator. When I do this in the calculator, I start with the fractions and then I work backwards. So 1 over 2 squared minus 1 over 3 squared. You can do that. Or you can do it in your head, 1 over 4 minus 1 over 9. You get the same answer. All right, let's multiply that by negative 2.18 times 10 to the negative 18th. So we get negative 3.03 times 10 to the negative 19th joules. Remember, the negative tells us that energy is released. So we're going to need to drop the negative. So we can say 3.03 times 10 to the negative 19th joules is released from the atom. And that's released in the form of photons. So we're going to use this, and we're going to say that the energy of a photon equals Planck's constant times speed of light divided by lambda. The question is asking us to solve for lambda. So you can rearrange this initially, which I think is what y'all tend to prefer to do, or you can not do that. Do it the other way. So we know that lambda is going to equal hc over E, and I'm just going to say P for photon. So 6.626 times 10 to the negative 34th. This is a good news because we don't have to define the joule here because we're not asking for speed or anything like that. Now, times the speed of light. 3 times 10 to the 8th meters per second. That cancels out the second. Divide by energy of the photon, which is up here. 3.03 times 10 to the negative 19th joules. Joules cancel out. We're left with meters. All right, so what I'm going to do here is I'm going to multiply that by -1. So I have a positive number. And if you have stored your variables, this is very easy to type in. So you just do HC divided by your previous answer, and you're going to get a nice number there. Make sure you read the decimal point. So 6.57 times 10 to the -7 meters. Or if you convert to nanometers, 657 nanometers. You do that by multiplying by 10 to the 9th, so 657 nanometers. Now, I don't expect you to know these specifically, but the 657 nanometers corresponds to the red line that you see on a hydrogen emission spectrum. All right, so let's do another one. Let's determine the wavelength of light that is absorbed when an electron goes from an orbital for n equals 2. So that's going to be our initial 2, n equals 5. So it's going to be our n final. So here it's increasing its energy level, so we need to be positive. Same process here. Delta E RH 1 over n final squared 1 over n initial squared. -2.18 times 10 to the -18th joules 1 over 5 squared 1 over 2 squared. Now here we're going to get a negative number. Multiply that by a negative, we're going to get a positive. So 1 over 5 squared minus 1 over 2 squared. See, there's a negative number. Times -2.18 times 10 to the -18th. So we're going to get 4.578 times 10 to the -19th joules absorbed. So when we use the words, we don't have to worry about the sign anymore. The sign can go away. In this case, it's positive, so that's okay. Now remember, lambda is Hc over energy of the photon. So 6.626 10 to the -34 joule seconds. 3 times 10 to the 8th meters per second. Seconds go away. Divide that by 4.578 times 10 to the -19th joules. We're left with meters. So HC divided by that final answer, 4.34 times 10 to the -7 meters, or 434 nanometers. Now 434 nanometer corresponds to a violet light. So if you shine a violet light at this wavelength, it's going to cause this energy level change. You won't see the energy level change. But if it goes the other way, when it falls back from 5 to 2, this is what you see. Now, you may have said, but Dr. B, we have like 7 principal energy levels, so N can be 1 to 7. Yes, that's true. And so sometimes, like if you run this for when N goes from 7 to 2 or something, you're going to get a much shorter wavelength, and that would go outside the visible light spectrum. So the only lines that we can see on a hydrogen spectrum are 4 wavelengths, and they correspond to different colors and different wavelengths. But others exist, they're just outside the realm of visible light. Again, as far as these calculations go, you will be given the equation, you will be given the constant, so you don't have to worry about memorizing those, but you do have to understand the concept of quantum numbers. Quantum numbers is the takeaway from chapter 7. Make sure you understand that first part of section 5.